it's one point to master student who implemented a transformation from eCore to groove graphs, and I could use that, but it gives me what you're seeing now. You're not even seeing it. Yes, you're seeing it now. So this would be the type graph, our type graph, or part of it. For the this is the specification language, and what you see here is that it blows up everything that occurs in eCore into way too many types to be really usable. So, for instance, it just reflects all the edges, the edge-like types in eCore into nodes in Groove. Here you see something that's actually a label type field of a check label, but there's an intermediate node, and I mean, even worse things happen when you have composite edges and things. So I spent some time. So this at least was an eye-opener, but clearly there's work to be done here. We should probably be able to tune this. I was wondering what other tools do. I mean, that's why I was asking you. Apparently, you have the built-in capability of reading XMI files, but either you have to restrict to a subset of what eCore can actually do, or you should have the same problem as we have. So I'm wondering about how you do this. Anyway, so I spent some time actually getting graphs that I could do anything with. In the end, I managed to do the on-off case, because the input of the on-off case then translates to something that is much smaller, which I think is a kind of picture that we've seen before. This is just a graphical representation of the input XMI file with the test cases and everything. And using rules of the kind that we have seen. So I can only, maybe just for contrast, this would be the rule that creates the change display action from an observe output in the input model. So what you see here is for instance, universal codification, which means that you do this for all instances of this node at the same time. What you see on the left-hand side is a set of all rules that are necessary, at least for the on-off case. So there are fairly few, and I think, as the GRGen people said, and I think this probably holds for more of the presentations, although it was not said explicitly. Typically, you have one rule for every construct in your input model. It doesn't quite work out this way because of the mapping not being completely obvious in all cases, but that's the kind of modularity that you can expect here, and that's just a feature of the problem mostly, and it does show up in the rules that you then need. So here's the create mode action, for instance. It does create one mode node that is then shared as the representation of all the mode related nodes in the input model. That's what you have the universal quantification for. So you see here something called an abstract mode. What is an abstract mode, you might ask? That's just a type, an auxiliary type that I created for the purpose of being able to do this. So in addition to the type for the specification language and for the configuration language, there's a glue type overlaid that allows me to introduce extra types just to be able to manipulate the model more easily. And here you see the abstract mode, which is a new super type for things that were already in the specification language, check mode, entity mode, observe mode. So there's how we solve that. Another question was about the ordering of the modes, and I probably took a wrong solution here. I now realize, because what I did instead, let me see where it is. It's the next action, I think. What I did is look for patterns like this, where you actually explicitly say that you go from one node to the other by pressing a button. I took those as the specification of the ordering of the modes, whereas others have really looked at the ordering of the test cases and took that as the defining order of the modes. I had a rule like that at first, and then I thought, okay, but it's actually much easier, because at least in this on-off example, you see explicitly two press button actions, and they do define a cycle of modes. So yeah, it's a question of how to interpret the exercise, of course, and I did it differently. As for the buttons, I don't have rules that actually order the buttons. The way it would have to be done is to insert into the graph model some way of having the strings ordered and then taking over the ordering of the strings. But that's typically the solution we've seen. Of course, it looks differently here because everything is graphical. So there is no rule structuring, or no scheduling of the rules, essentially, except that you see some priorities here. What are they for? Well, I need one rule that actually deletes everything that has to do with the specification model in the end. Otherwise, we'll get something that combines both, and that is not something that is somehow implicit or built into Groove, because that's not the sort of thing we typically solve. So that's a low priority rule that applies when everything else has been done. And there's one high priority rule which I just inserted as an example of a sort of check you could do underway, sort of sanity check, which this tests for a mode having two distinct successors. And because it's a high priority rule, if it applies, then it stops the whole transformation. You can immediately see that something went wrong here. So that's why so one high priority rule, which could be more if you have more of these invariant checks, and a low priority rule to make the model correct. And then the actual functionality of Groove is to build state spaces. So what you can do here is just explore the entire development. Now, why does it stop here? Because I was testing on another input model. So back to the LTS, you can explore. These are the individual next possible states. It doesn't make much sense in a model transformation setting, because everything should eventually be confluent and end up in the same model. But that's because we're just interested in different sort of problems essentially, but we're still curious how it works for this kind of problem. So on the left hand side, you always see which of the rules are applicable. You can try them out. You can look at the individual states, what it has become, or you can then, if you're tired of this, do the rest of it automatically. I think I should restart and then do it automatically. Now what happened? Something went. This rule should not be there. Now I hope I don't get a demo effect anymore. No. Okay, so you see in 11 steps you get to the end result. The last rule is this delete spec, which removes everything that has to do with the specification nodes in the. No. Yes? Okay. If we go here, then the rule is applicable, and what it does is it removes everything that has to do with the specification language, which are now selected. So if I apply this and everything is gone, I'm left with just the configuration model, which is the one that everyone came up with, except that I don't have it in XMI, so I can only go to you as a graph. But I thought it was good enough to just tick belatedly my entry on the blackboard. Okay.
Great, thank you. Any questions?
It's never good.
So I had a question actually, if nobody else had something. Oh, go on.
So can you actually use the state space exploration to check the confluency of the rules?
Yes, in this case you can. I think. Well, not of the rules. Okay, now I think I set it to a linear exploration. Yes. So if I do instead the breadth first, and you see that indeed, at least for the example, it all boils down to one unique target state, which is what you of course want. So it's not a true check of the confluence of the rules, but only for this example, of course. But still, it gives you some confidence on that things are actually correct. But yes.
Anyone else?
Yeah. So maybe you're actually right in choosing the tool for the job, because in some cases in QVT, in some semantic interpretations of QVT, you need to do some backtracking or some cleverness. When there are a lot of when and where constraints. I think there's some paper of Perdita Stevens that says that something somewhere, sometimes you need backtracking because it's not always clear.
Why does give you the opportunity
semantics to interpret it further, something like that.
A nice thing of this feature of state-space exploration that does help here also is it gives you debugging capabilities, obviously. So, and that for me at least was also useful when developing these rules. So yes, I prepared a few slides, but I think I told this for me is the main outcome of this particular workshop. Really, we have to look at this again. I I think there's at least one more master thesis, room for one more master thesis. So maybe Ivan, if you're interested in this, where it should be fine-tuned. So, it's nice to be able to cope with all e-core features, but if you don't need them, then as you see, it blows up things. So you really want to be more, how do you call this? Less expensive.
Great. So there was a question that might be useful because it's more of a clarification than anything else. So you showed us a check that was executed partway through this high priority rule. So this causes the transformation to stop. So this is a different approach to sanity checking to the one that we saw earlier for I think the Gretel solution, where they check before the transformation executes. This is kind of live as the transformation is running. Okay, great. Yes. Yeah. I just wanted to make sure I understood.
Sure.
Yeah. Okay. If there's nothing else, then I think we're done.